Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I was discussing about the different controlling factor to design the stone column improved ground to mitigate the liquefaction hazard. Okay. So, now today's lecture I will continue from where I end in the last class, that this is the your excess water pressure developed due to n number of cyclic shear stress or stress cycle application, and in equivalent the number of uniform stress cycles and number of stress cycle needed for initial liquefaction. Okay. So, that means here it is the number of stress cycle developed during earthquake versus the number of stress cycle required to cause the liquefaction. That is my second term, and in my first term it is the spacing versus diameter or diameter versus spacing, and here TAD is the KH. What is KH? KH is the horizontal permeability of the soil. Okay. So, now if I write what is this terminology, I have mentioned that this is TAD, which is your KH divided by gamma W, and TD divided by MVS into RD square. So, where MVS is the coefficient of volume change in radial direction. Of the soil. Okay. And these things I can further write as CR into TD divided by DRD square. Okay. So, where you know that CR is equal to KH by gamma W into MVS, where CR is the coefficient of radial consolidation. Okay. But here there is a here it is coefficient of radial consolidation, you can see, but there is, you can see in the actual radial consolidation it is your the H square. Okay, that it is CV into CV into T divided by H square, and here it is TD, where TD is the duration of earthquake, and KH is the permeability of soil, that is radial or horizontal. Okay, and gamma W is the unit weight, and RD you know the diameter of the drain. So actually in the CR value, you can see this is coefficient of radial consolidation, it is okay, and then in the TAD it is mentioned, it is non-dimensional by RD square, not RE square. Okay, generally this is TAD is the time factor basically. So in the consolidation vertical one, it is non-dimensional by, it is expressed by CVT by H square. Here it is, H is the drainage path, but here remember that here TAD is been written not in the drainage path, but in terms of your diameter of the column or the radius of the column. So that means here this is TAD is gamma H by KH by gamma W into TD MBC RD square. R is the radius of the drain, remember that. So that means basically these three terms, those are the functions, are duration of the earthquake, number of cycles required to cause liquefaction and applied during earthquake, and the spacing to diameter, in addition to the soil parameters. Obviously soil parameters are also function, because TAD soil parameters are also there, permeability of the soil is there. So these way we can represent that, and then based on that Seed and Booker provided these design charts. So later on I will discuss example problem and I will use these design charts. Here you can see these there are 4 design charts. This is N equivalent by NL equal to 1. This is 2, this is 3, this one is 4. You can see this is 4, this one 3, this is 1, this is 2. And why? That's why we are using the stone column, no? So that we can apply more stress as compared to the apply more cycle as compared to the cycle required to cause the liquefaction. Even we can design it the 4 times more than the number of cycle required to cause the liquefaction. This is for exactly the initiation of the liquefaction without applying your any improvement technique. The first one, just liquefaction has been initiated. Second one also is valid, because here liquefaction will not occur because we are providing stone column. It will dissipate the excess water pressure. In third, in fourth also we can do. And the x-axis is RD by RE, that means the diameter of the drain divided by equivalent or the radius of the drain divided by radius of the equivalent influence zone. And y-axis is the RG, or you can say it is RU also, RU or RG, or in later on I will use the U max. These both are same. These are equal to del U divided by sigma V dash. Okay, this terminology is same. So that means here if I know that under which U I will design our system, and if I know the TAD, then I can determine this ratio. Then from there I will get my design parameter. So I will discuss how we will use this chart. So that means this is TAD, you can see from 200 to 2. This is also TAD. TAD expression I have given. What is TAD expression? This is the TAD expression. Okay. So now here one more thing I want to mention, that in this approach you can see what are the parameters are being used. The parameters are being used is the MVS, which is the coefficient of volume change in radial direction for the soil. Then KH, it is also for the soil. Horizontal permeability of soil, KHS if you say. Then so that means the only the permeability of the soil and permeability and the compressibility of the soil are being considered in the analysis. You can see. So that means here another important assumption is considered in this analysis, that your permeability of the stone column is infinite. So that means the boundary condition will be that whenever at this point the boundary condition, your del u is equal to 0. At the interface between the soil and the column, the boundary condition is del u is equal to 0, because your permeability of the column is infinite. So whatever the boundary water will touch at the boundary between the column and the soil, then it will vanish. There will be no water pressure inside the column, because it is infinite. There will be huge permeability, so it will be 0. So if you consider that assumption, then your boundary condition in between the column and the soil will be that water pressure will be 0, del u value is equal to 0. But in the field, as I mentioned, that okay, the permeability of the column is more than the permeability of the soil, but it is not infinite. There is a finite value in the field. So that means we have to incorporate the permeability of the column in the analysis also. Okay. So that's why in the next stage we will incorporate the permeability of the column, because we have discussed my 4 cases. Previous lecture, you see the stiffness of the column is greater than stiffness of the soil, and permeability of the column is greater than the permeability of the soil. So we will consider that permeability of the column. Next one, we are telling that the stiffness of the column is more than the stiffness of the soil, or compressibility of the column is less than the compressibility of the soil, but these parameters is not considered in this analysis. It is only the compressibility of the soil is being considered. So there is a need to consider the compressibility of the column is also need to incorporate the compressibility of the column also, so that we can incorporate the stiffness effect of the column. So that means what are the things we should incorporate in this study? We should incorporate the permeability of the column, because as the permeability is not it is obviously more than the column, it is not the infinite. So there is a need to incorporate the permeability of the column. Then here the stiffness effect of the column is not incorporated in this analysis. So there is a need to incorporate the stiffness effect or compressibility of the column. And third one is the densification effect. So that means the smear effect. Here also it is not been incorporated. You can see that means the densification effect, because of that the permeability and the compressibility of the soil surrounding the stone column will be less than the permeability and compressibility of the undisturbed soil. So those are also not been considered in this analysis. So in the next stage we will consider all these effects, and then we will develop further or modified design charts. So different researchers have worked on this area to incorporate those effects. So you can get their study, those are available. So it is from basic approach is by Seed and Booker. After that, different researchers have worked to incorporate the permeability effect, to incorporate the densification effect, okay, in their analysis. So I will discuss few of the papers which is been published by me and my students. So I will discuss few of the work related to this area, but doesn't mean that these are the only works. There are the other works are also there. You will get, if you go through these literatures, those I have given, these 3 references, there also you will find more other work where the permeability effect, densification effect are already been incorporated. So I will discuss few of these references where we have incorporated, or the effect of stiffness, permeability and densification as well as the clogging effect has been incorporated in this analysis. So now if we incorporate the stiffness effect, the detailed analysis and the parametric studies you will get from these references. I have given these references, you can see on the screen. So if you read this paper you will get more information, but I am summarizing the important findings from these papers, that if we incorporate the stiffness effect of the stone column, then the maximum pore pressure ratio, pore pressure ratio means RU, is decreased by 20 to 60 times. So that means stiffness effect will act as a positive effect, because it will, if we incorporate the stiffness effect, then it will decrease the pore water pressure ratio by 20 to 60 times. So it has a positive effect. Okay, so that means we can incorporate the stiffness effect. Then another one, smear effect can increase the Umax here, basically Umax or RU, so both are same, or RG, value by 10 to 16% depending on the amount and extent of the disturbance. So because why? That if your permeability and the your permeability increases, whenever you are talking of the stiffness effect, it has combination of two effects. One is the your permeability of the surrounding soil decreases, another your compressibility of the surrounding soil decreases. Clear? So, and it has been observed that in the smear zone, the permeability reduction has more significant effect as compared to the reduction of the compressibility. So, as if we are saying that it is a combination of two effects in smear effect, that because of densification, then permeability is also reducing, compressibility is also reducing, but the permeability reduction has more significant effect. So that means because of this reduction of the permeability, so your this water will travel from the soil to column, and if some portion of the soil, if permeability is reduced, then it will take more time to dissipate this excess pore water pressure. So its performance, drainage performance will be reduced. So, and if the drainage performance will be reduced, then the RU value will increase, because if you consider the stiffness of the stone column where the drainage performance is been increased, that's why the RU value is decreased. You can see that's why the RU value is decreased by 20 to 60%. But due to the smear effect, your drainage performance will be decreased. So that means RU value will increase. So that's why the RU value will increase by 10 to 16%, 60%. Smear effect increase the peak RU value. Okay, so and that depends on the extension of the amount of the disturbance or the densification effect. So now these are the important findings. So now you can see that this chart is showing the effect of different your mechanism, that you can see that first we are talking about this chart. So if I explain this chart, x-axis is the non-dimensional duration of earthquake, and 1 means this is the end of earthquake. So that means initially the pore pressure will generate, and that's why this is your RU value. Umax is the RU. So this is your RU value. It will increase, and it will increase, reaches the maximum value at the end of earthquake. Then it will dissipate. So it will decrease the value. So remember the meaning of this curve, that this is 0 is your starting of the earthquake. So that means it will start and your pore pressure will generate, okay, and at the end of the earthquake it is maximum. After that there will be only dissipation of the water, so pore water pressure. So that's why this value will RU value will increase, reaches maximum at the end of the earthquake, then it will start decreasing, and then it will become 0 or close to 0, because as you have provided as drainage path. Now the question is that during the earthquake, so that means from 0 to 1, T value 0 to 1, this is the duration of the earthquake. So, during the duration of earthquake, it is simultaneously your pore pressure will generate and dissipate. It is not only the generate, because you can see it is increases. Actually, it is RU value is pore pressure is generating as well as dissipating during the earthquake. Okay, but the net effect is your generation is more compared to the dissipation. So that's why this is the net value, and that will increase. So RU value, this is the net, because it is simultaneous dissipation and generation during the earthquake. But after the earthquake, it is only dissipation, no generation. Clear? So that means during the earthquake, it is dissipation and generation of the pore water pressure, but the generation of pore water pressure is more than the dissipation of pore water pressure. That's why your net RU value increases and it reaches maximum at the end of earthquake. But when the earthquake is over, then it is only mainly the dissipation, not the generation. Clear? So that's why your RU value will decrease and it will become 0 or close to 0. So now if I explain that, you can see this graph. This is the black dot graph. This is the graph where no effect is been considered. No stiffness effect, no permeability effect, no clogging effect, no smear effect. So this is the curve. This curve is same as the Seed and Booker curve, T versus RE. Now if I consider the permeability of the stone column, because in this curve you can see the first case without any effect, your permeability is considered as an infinity. But here the permeability is taken as finite, and generally the permeability of the column is taken, if you take it, is 200 to 300 times more than the permeability of the surrounding soil. 200 times to 300 times, not the infinity. So here it is been considered as 200 times more than the permeability of the surrounding soil. Then you can see the same analysis. Here RU value is only 0.2. That means there is no possibility of liquefaction or initiation of the liquefaction. But if I consider a finite permeability, then you can see the same analysis will go to 1 or greater than that. That means the liquefaction has been initiated. So that means because of not considering the permeability or finite permeability of the column, that one case the pore water pressure value is 0.2, but here oil resistance means considering the permeability of the column, that is called oil resistance. And if I consider the permeability, then this RU value reaches 1, that means the liquefaction possibility is there. Whereas not considering finite permeability, there was not the possibility of liquefaction. Now next one is the oil resistance, that means the permeability of the stone column is being considered, plus the stiffness of the stone column. As I mentioned in my previous slide, the stiffness of the stone column has a positive effect, so your RU value should decrease. Here it is mentioned, you can see RU value decrease by 20 to 60%. So you can see that for this particular case, this is my oil resistance curve. Now oil resistance and plus the stone stiffness of the column, this yellow curve, so it is been further decrease because of consideration of stiffness of the stone column. So it is, there is a decrease around you can see 20 to 60%. So this is the decrease. Next one is the oil resistance plus stiffness plus smear effect, and smear effect is negative effect. So because of smear effect, RU value will increase by 10 to 60%. So you can see this is without any considering any effect, this black line, without considering any effect. This is considering the permeability of the stone column. Okay. This is considering permeability of the stone column plus stiffness. So because of the stiffness, your pore pressure will reduce from 1 to around 0.55. Then when we consider, this is the curve, when we consider the smear effect, then from here it will further increase because smear effect has the negative effect. It will increase the pore water pressure, and that I have already discussed. So that means it will go here. Now the last one is the oil resistance plus stiffness plus smear plus clogging. If I consider all this flow effect, then you can see very interesting result that this is the curve, that means this is the purple color and green color. So this is the green color curve and purple color curve up to t equal to 1, they are overlapping, which means that the clogging doesn't have a significant effect during the earthquake, because during the earthquake there will be dissipation also, but because of that dissipation there will, because it will, the clogging, it has to take certain time to, because we have to give some time to this fine particle to block the pore of the columns, then the clogging will be effective, or the clogging will start and it will affect the result. But during the earthquake, this small period, it is not getting sufficient time to clog. So that means that during the earthquake, the stone column, their clogging is not that significant. I am not saying nil, but not, because there is still some dissipation of the pore water pressure, but that is not significant. But if you see that after the earthquake, the t equal to greater than 1, that means after the earthquake, this is the end of earthquake, this line is the end of earthquake. This line is the end of earthquake. You see, and this is your beyond the earthquake, less than, greater than 1 is the beyond the earthquake, and less than 1 is the during the earthquake. And after the earthquake, you can see this purple line and this green line, they start deviating. It means that when the dissipation of the pore water pressure start, then the clogging is occurred, and that is significant. And you can see after that, your without clogging curve, this green curve, here this RU value will reach to 0 or close to 0 very small time, within very small span of time. But if I consider the clogging, then you can see RU value is not close to 0, even at t value, non-dimensional time is 3. It is not close to 0. That means you can see, that means here, but it will reach or close to 1, but it will take a huge time. So that means that because of the clogging, your drainage performance will be reduced, but that will not make a significant effect during the earthquake, but it will make a significant effect after the earthquake, and it will basically increase the time to dissipate the pore water pressure, if I consider the clogging. So it is clear all these 4 effects. That means if you consider the permeability of the stone column, then your pore water pressure value will increase. If you consider the stiffness along with permeability, your pore water pressure will further decrease, because stiffness has a positive effect. Then if you consider the smear effect along with permeability and the stiffness of the stone column, then the pore pressure value will further increase. And now if you consider all the effect, permeability, stiffness, smear and the clogging, so up to the during the earthquake, this permeability, clogging, smear and smear stiffness curve will be same as, the without clogging curve and with clogging curve will be same up to during the earthquake or duration of the earthquake. But after the end of the earthquake, if I consider the permeability, so your dissipation time of the pore pressure will increase because of the clogging. So now you can see that phenomena is very important, that this is, we are talking about your first earthquake. Now the first earthquake, during the earthquake your permeability is not that significant, but after the earthquake the permeability will during the earthquake clogging is not significant. we have observed here. So that means after the earthquake, the clogging will play a significant role and it will increase the dissipation time. Okay, but that clogging will still be there if a second earthquake comes. In that case, during the earthquake also, the clogging will play a significant role, because these columns are already been clogged after the first earthquake. So now if a second earthquake comes, if this clogging because of this clogged column, you can see that your RU value will increase. This is even during the earthquake. It is for second earthquake. And after that, for the first earthquake, you can see during the column earthquake during the earthquake period, it is not, clogging is not that significant, but after the earthquake, the dissipation time will be more if we consider the clogging effect. But second earthquake, even during the earthquake, it has a significant effect on the pore water pressure. Now, so based on that, some design charts are also being developed. So in the next class, I will discuss example problem, and I will show you that how these parameters can be incorporated in the design, and to design a stone color improved ground by using that example problem, for both for seed and Booker approach, and without considering any effect and considering the effects, and then you will see how much difference will come in the design parameter. Thank you.